Hello and welcome to our lesson on graphing complex numbers. The graphing of complex numbers we're going to do is in rectangular form and then in trig or polar form. So let's start with the rectangular form or the standard form. So the standard form of a complex number, which we've reviewed, that is our a plus bi. So we know our complex number has that real number part of it, has that imaginary number part. So that standard form for a complex number is also called rectangular form because it's something that we can try to represent graphically in our rectangular or our Cartesian coordinate system. So this complex number can be graphed in that system, in that Cartesian coordinate plane, by making a modification to our axes. So what we're going to do is call the horizontal or the x-axis the real number axis, the real axis. And then we're going to call the vertical or the y-axis the imaginary number axis. Then we have a place to again, visually represent each of the components in our complex number. So what we're going to do after modifying those axes is make the complex number or represent the complex number by a vector, a position vector on that graph. So specifically what we're going to say is that our complex number, now because we're going to put it in the rectangular coordinate system where we're generally dealing with x's and y's, so vertical and horizontal movements, instead of calling it a plus bi, we're going to call it x plus yi, but it functions the same way. So a just being replaced by x, and then the imaginary component there, bi, being replaced by yi. We're going to represent this graphically in this rectangular plane by saying that it's going to be a vector that starts at 0, 0, that's what a position vector does, and then ends at the point x, y. Now that might not be making a whole lot of sense, so let me try to visually explain everything I just said. So again, we're going to call this horizontal axis the real axis, and we're going to call the vertical the imaginary axis. So when we're graphing a complex number, what we're going to be graphing is a vector in this plane, a position vector in this plane. So remember, position vector starts at the origin, and then it goes some distance, okay? So in this case, the distance is going to be some distance along the I'm trying to change colors. Along the horizontal axis here, that distance along the horizontal axis is going to be the real number part of the complex number, and then we're going to be going some horizontal distance, which is going to be the imaginary part of that complex number. So the point that we land here, we're actually going to call this point z. So it's z used for our complex numbers is again going to have an x plus a yi piece. Okay, so if I added that x and y together, then that's where we land. So we're going to go again along the real axis, x increments, and we're going to go along the imaginary y-axis, right, y units. And we can, again, call this a vector. In vector form, we're looking at the vector x, y. So even though we have that imaginary component, we're reading it just like we would read a y value. So if, again, our imaginary, let's say we had like a 3 plus 2i deal. So 3 along the x-axis, just like we normally would, 2 along the imaginary axis. So an x value of 2 and or an x value of 3 and a y value of 2. So we have that imaginary there just to tell us it's the imaginary axis, but we read it just like we read the y value in front of that piece. Okay? So this is sort of the picture that's happening here. Again, reading an x and a y in a vector, just like we would read, x and y in a normal point. It's just the y is now the imaginary axis. Okay? So let's try to graph a couple of these, really, really simple. So 2 plus 3i, similar to the example I just showed you, again means in a a vector, we'd be looking at going an x value of 2 and a y value of 3. So we want to just pick out these two numbers. Again, our x value, still an x value, and our y value is now on the imaginary, but it's still a y value. It's just going along what we're renaming the imaginary axis. So if I was to graph this, I know that it's going to be a vector and it's going to land at 2, 3. So I want to go 2 on the real axis here. So I want to go positive 2 on the real axis, and then I want to go positive 3 on the imaginary axis. So that'd be right 2 and up 3. This is where my vector should land. And so this, oops, turned my eraser on. Again, is going to be my vector starting at the origin and landing here. That's going to be what I called A, okay? So again, if I was going to graph negative 3 minus 5i, really it's going to be a vector that goes negative 3 and negative 5. So when I go to graph, oh, I should probably change colors here so you can see where I'm going. Let's make this one red. So again, we're going to go negative 3 on the x, negative 5 on the y. So if I go negative 3, negative 5, that's where that vector should land. And so I'm going to draw that vector in there, and that's what I called B on the paper. And then the last one, notice we only have an imaginary component. Remember, every number has a complex form, so this is the same as 0 plus 6i. If you don't see the real number part, it's just zeroed out. So as a vector, we're not going to move along the x-axis. We're only going to move up the y-axis. So as a vector, it'd be 0, 6. That's the landing point for this vector. So 0, 6. And 1, 2, 3, 4, 5. Oh, why did I make that 6 and I didn't even make a graph that fits 6? How about I just change that? How about I make it 5, and then we can make this 5, and then it fits. So then we'll do that, and this will be, again, a vector here that lands at that location, and we're going to call that C. Okay, so graphing a complex number in the rectangular or Cartesian coordinate plane, again, is just graphing a vector, a position vector. So we start at the origin, and we use the x and y components to tell us how to move from that origin, okay? Now the trig form of the complex number is a little more complicated. The trig form of a complex number is also called its polar form. Okay, and the polar form uses different components. So in our rectangular form, we're looking at something that's in terms of x and y because that's what our rectangular plane is in. Now in a polar form, remember polar coordinate system, our points are all in terms of radius and angles and thetas. So that's what we want here. The polar form for our complex number is going to be in terms of some radius length and some theta. So to make the connection here, we got to remember how x relates to r and theta, how y relates to r and theta. So this came up in our previous topic. We know that x can be found by multiplying the radius by the cosine of theta, and we know that y can be found by multiplying the radius by the sine of theta. So I actually want to use those two things to rewrite a complex number. So let's say we had our complex number in our standard rectangular form, again our x plus y I. If I replace x with r cosine of theta and I replace y with r sine of theta, then I can get my trig or polar form of this complex number. So I'm going to replace x with r cosine of theta, plus I'm going to replace y with r sine of theta, and it's being multiplied by I. I want to make sure that I'm multiplying r sine of theta by I, that whole value by I, and not the theta. So I'm actually going to rearrange that. I'm going to put the I, oops, that's supposed to be a plus. I'll put the I in front of the r sine of theta again so that it's clear I'm not actually multiplying theta by I. I'm multiplying r sine of theta by I. Now, if we look at this expression, we can clean it up a smidge because these two terms have an r in common. We can factor that out. So we end up with r times the cosine of theta plus I times the pen froze. There we go. Sine of theta, and that is, again, in terms of r and theta, but we still have the imaginary in there. This is what we call the polar or trig form of our complex number. So if we have a complex number, again, x plus y I, the related polar or trig form is going to be defined as r times the cosine of theta plus I sine of theta. So again, this is our rectangular form, and this is our polar or trig form. And remember, both of these, technically, I called this z earlier. I could do that here as well. I could say z equals. You'll see z in there sometimes. If you didn't have that notation, though, it wouldn't be the end of the world. And now this second one, this trig form, the polar form, actually has an abbreviated version. So sometimes you'll see the c, I, and the s from the cosine, the imaginary, and the sine as an abbreviated form. So the abbreviated form, oops, I can spell, I promise. We would say that z, abbreviated as z equals r, and then cosine, imaginary, sine of theta. Okay, so r cis theta when we're reading that, where again that's the cosine, the imaginary, and the sine of our theta. So I really like this abbreviation because it's a lot less to write, but if it looks confusing to you, you absolutely don't have to use that. Okay, so either one of these would be perfectly acceptable. Now, let's see if we can't actually take one of these polar forms and graph it. Flip it over here. Okay, so if I want to graph a complex number in its polar form, I just have to understand what this is giving me here. When I'm looking at the polar form, we just said that this number was going to be the radius, and that this number here was going to be our angle. Those are the two things I need to be able to graph my polar coordinate, right? So if this is the complex form of my, or this is the polar form of my complex number, in the polar plane, when I go to graph, again, I need to know the radius right here. So I know my radius is going to be 5, and I need to know my angle. Again, that's given to me as 135 degrees. So I'm going to plot this point, this complex number. I'm going to graph this complex number at an angle of 135 degrees with a radius of 5. So 135 degrees with the radius of 5. 135 is here. Radius of 5 is here. So again, we're at an angle of 135 degrees, but we only want to go out to a radius of, I want to do that. I want to continue recording. And so, if we want to put that radius in, we can, but it's implied because we've gone out that distance. So that would be the location for D. That is what the graph of our complex number in the polar system looks like. Okay, crazy. This seems so different from things we've done before. Okay, so same thing here for E. If this is our polar form, then it's telling us right here our radius is going to be a 9, and that our angle is going to be 330 degrees. So we're going to go to 330 degrees. That's going to be over here in quadrant 4, and we want a radius of 9, so we're going to end up landing here, and that's what I called point E. And again, that whole radius, we could highlight that as part of the graph if we wanted to, but not necessary because it's given because we've gone out that distance. And then the last one we see here, let's go pink. We have a radius of 4, and then we have an angle given to us as a negative 135 degrees. Now we are explicitly dealing with positives in this picture, but we know the negative just means go the other direction. So this angle, negative 135, if I added 360 to that, so remember positive 135 is here, I want to go that same distance in the opposite direction, and that would take me to the coterminal angle, which would be 225 degrees. So 225, and then again a radius of 4. So 225 here, radius of 4 here, and that would be the location for for f. Okay, so again, if I was to ask you to graph that complex number in its polar form, that is what the graph looks like. It is that point which has that specific radius on that specific angle. Okay, so the graphing actually isn't too bad. It's understanding what you're looking at and being able to go from one form to another. Okay, so let's try a few more problems just to make sure we can sort of read what's happening here and understand all of the information. So looking at this next problem, it says use the given graph of a complex number to give its rectangular and polar forms. So I have a vector in here. I'm told that vector represents a complex number. So let's start by writing its rectangular form. I think that's going to be the easier of the two. So let's go to blue. The rectangular form, remember, means we need x plus y I. So I need to know how far I'm moving along the x and how far I'm moving along the y. And I could see this in two ways. Like, remember, I can use the endpoint here. That location is at 8 and 8. So if that's 8 and 8, my vector form is 8 and 8. That means that's my x, and that's going to be my y. Well, in this case, it's yi. You can also just count it out. So you're moving this much along the x-axis, 8 units here, and then you're moving that much along the y-axis. So remember, this is like our imaginary, and this is our real. So if we're going 8 units here and 8 units here along the imaginary, then the rectangular form is just going to be 8 plus 8i. So that would be the rectangular form. Done. Okay? The polar form is the one that requires us to know r, and it requires us to know theta. So r, we can see that in this picture. That's the radius length here. Color. So that's the radius length here, and again, it requires us to know theta, which actually isn't too terrible. If we know this is a right triangle, okay, now I put I in here just because it's on the imaginary axis, but technically this side length is 8 here. And if the two sides of that triangle have equal lengths, if those sides are equal, their angles are going to be equal as well. This is a right isosceles triangle, in fact a 45, 45, 90 triangle. So I can tell by looking at this that theta has to be 45 degrees. We have to have 45 degrees here because, again, if these two are equal, these two are going to be equal. So I don't even have to do any work to know that theta has to be 45 degrees. And then the radius, I could use Pythagorean theorem, but again, I shouldn't have to because this is a 45, 45, 45, 90. If this is a 45, 45, 90, remember my hypotenuse is my side length times a radical 2. So I have enough information without really having to do any work to get that polar form. I know my polar form, again, is r, and then cosine of theta plus I sine of theta. I just found r was going to be 8 radical 2, and then I found theta was 45 degrees, and so that would be my polar form. Now, if it wasn't obvious to you, that was a 45, 45, 90, or that radius length there is 8 radical 2, could you do the work? Absolutely. And you would do that using the connections we've talked about already. We know that x is r cosine of theta. We know y is r sine of theta. We know how to find the radius using Pythagorean theorem. We know how to find the angle using the inverse tangent. So I can show you here. Again, if I wanted to find I think this would be the easiest piece that I could find using Pythagorean theorem. So I could say 8 squared plus 8 squared would be equal to r squared, or r squared would be equal to 8 squared and 8 squared. So I end up with 64 and 64, and that means r would be the square root of 128. And if we were to break down the 128, guess what's going to happen? We're going to end up with 8 radical 2. And if I wanted to figure out what theta was, I got inverse tangent to do that. And so I said my theta would have to be the inverse tangent of the opposite over the adjacent. and so we end up taking the inverse tangent of 1, and that's going to happen. We're going to get inverse tangent, well, tangent, we're looking for an angle where the tangent's equal to 1 that happens at our 45-degree angles. Now it's got to be positive. Technically that happens in quadrant 1 or quadrant 3, but we can see clearly here we are in quadrant 1, and so again that leads us to that theta of 45 degrees. So if we needed to do the work, we absolutely could, but hopefully when your picture gives you enough information, you can avoid some of that work. Now, sometimes work is not avoidable, so we're going to try some similar work here just without the picture. In number 2, we are trying to, we're given the rectangular form of a complex number. We're trying to write that complex number in its trig form. But again, to write my trig form, that's this guy here, I need to know 2 things. I need to know what is my radius and what is my angle. So based on this information, remember, if this is my rectangular form, then I know that x is going to be a negative radical 3, and that y is my coefficient of I, which means y is going to be 1. So if I know x and y, I should be able to figure out r and theta. I know that r, my radius, again, square root of x squared plus y squared, and so that ends up being the square root of radical 3 squared is going to be 3, 1 squared is going to be 1, and the square root of 4 makes 2. So radius is going to be 2. And then to find our angle, remember, inverse tangent. So inverse tangent of our y value over our x value. So now we just have to figure out where. Now, we could try to use the calculator for this. Actually, we could use the calculator for this, but remember what we want to do is try to get exact values from the unit circle when that's possible, and that's going to be possible here. We're looking for our tangent, which is our y over x, to give us 1 over radical 3. So that's going to happen when we have 1/2 and then negative radical 3 over 2 here. That negative attached to that radical 3, that's why I put that on the bottom. So where do we have coordinates of negative radical 3 over 2 and positive 1/2? That's the question. So we're looking in the unit circle for a negative x and a positive y. That's going to happen in quadrant 2, which makes sense because this is in quadrant 2. So in quadrant 2, where does that happen? Let's see. This is our 30-degree reference angle. This is 150 degrees. I'm assuming you have a unit circle handy, but that's going to happen at 150 degrees. Oh, maybe I shouldn't have erased that. So theta going to be 150 degrees. Now it doesn't specify here whether to put this in degrees or radians. If it doesn't specify, it doesn't matter. If we need it to be in radians, that would be, this again, it's a 5 pi over 6. My brain was trying to think that out. 5 pi over 6 radians. So then our trig, or our polar form, we could write a couple of different ways. Let me move this. So here are some options. I could say that z, if I want to just call it z, and really this could have been called z here, is equal to my radius of 2 times the cosine of my 150 degrees plus I times the sine of my 150 degrees, if this is in degrees, or the abbreviated form would be 2 cis 150 degrees. Or, if I wanted to put this in radians, I could say z equals 2 times the cosine of 5 pi over 6 plus I times the sine of 5 pi over 6, or again, the abbreviated would be 2 cis 5 pi over 6. Okay, so all 4 of those answers would be perfectly acceptable. If it specifies degrees versus radians, then obviously you'll pick, but even then you'd still have 2 different options. Okay, last one, we're just going to go in reverse here. This time I have my complex number given to me in trig form, so I want the rectangular form. So in this trig form, I'm recognizing that my radius is 2 and that my angle is 300 degrees. So to get my rectangular form, I need to take r and theta and figure out from those what x and y are. But we remember that x is r times the cosine of theta, so r times the cosine of 300 degrees, and that's going to be 2 times, let's see, cosine of 300, that's a 60 degree, that's a 1/2, but it's in quadrant 4, so that's still positive, so 2 times a half, which means our x value is going to be 1. And then we know our y value. Our y value is 2 times the sine of theta, so 2 times the sine of 300 degrees. So again, that's a 60 degree reference angle. The sine at 60 degrees is radical 3 over 2, but since this is in quadrant 4, that's going to be negative. So this ends up being 2 times negative radical 3 over 2, which means those 2's are going to cancel and leave us a negative radical 3. So the rectangular form for this would be 1 for the real number part, go back to a different color, would be 1 for the real number part, and then a negative radical 3 for the imaginary component. So that would be our rectangular form here. And I didn't box all this in, but technically all 4 of these are answers here. Okay, we did it. Hopefully you have enough to get going on your assignment, but as always, if you need any extra help, just reach out. Until next time, take care.